Very good morning. Hey, very good morning. So it's 8:15 and time to get started. So it's a week number 7, last lecture week prior to midterm exam. And what happens today is that I'm gonna discuss or keep on discussing about modal reduction techniques. And today I'm gonna introduce you a very often used modal reduction technique, which is called Crankshaft technique. Um, it's a kind of like an alternative way to conduct an eigenvalue analysis, and it produces certain advantages regarding how to produce a deformation modes for modal reduction technique. And once we're done with that, then I'm going to spend quite a bit of time. Hopefully, next, first 45 minutes is about this modal reduction technique, and I'm hope that the other 45 minutes is about how to prepare yourself the midterm exam. And this midterm exam is something that we need to discuss a little bit about the details. And that's simply because yesterday I checked how is exam scheduled from LUT administration website or student affairs office website, and I was unable to find any particular time for a midterm exam. And that means that we need to make an agreement when we can organize this midterm exam. But anyway, so that's going to be after first 45 minutes, which covers the modal reduction technique. And then let me see, let me just put my comment window visible to me. Okay, so that's about it. So with that, so let's get started. And let's get started in a classical way. So that's us. Let's summarize what is that we discussed a week ago. And a week ago, now this is going to be very important explanation for you, particularly when you're preparing yourself to midterm exam. So this whole discussion is somehow related to the floating frame reference formulation, the floating frame reference formulation. And remember that the floating frame reference formulation is something that you describe the deformation in a way that if you have a body, potato shape body here, then you have here body reference coordinate system. And with help of the body reference coordinate system, you describe a particle P here. So the particle will be described by vector U bar. And now what we're going to do in a floating frame reference formulation is that we're going to add something to this vector U bar. And because we're going to add something to vector U bar, we're going to denote the original vector U bar by vector U bar 0. Okay, so what we're going to add to this vector U bar, this by the way is assumed to be constant. So this is just simply defining where the particle is located on its original configuration. So original configuration is like a matter of agreement. Once we have this agreement, then we cannot change it anymore, meaning that this vector U bar 0 is constant with respect to body reference coordinate system, with respect to this coordinate system here. All right. Now, because we want to describe the deformation, the vector U bar 0 is unable to describe the deformation, so we can add one more component there, and the one more component is called U bar F. U bar F that describes the flexibility. Now, when using this kind of kinematics and when considering that everything have to be described with respect to global coordinate system, we eventually are able to express the kinematics in a way that we have here the component that describes the translation. So the component that describes the translation. Then we take orientation of body reference coordinate system into account. And that is then multiplied by two components of vector U bar. Vector U bar 0 and vector U bar F. And all that, when you put all that together, then you're able to describe where the particle is located with respect to global coordinate system. So that's the concept. That's what the concept is about. Now, what we need to do then is that we need to take a full look, close look to this guy here, vector u bar f. How is it we can describe this deformation? Now, we agreed earlier that the easiest way to do that is to use a finite element method. In a finite element method, what you do then is that you discretizing entire body by number of elements. And elements then in turn are combined together in nodes. So we can have different kind of elements. So we can use a beam-like elements that are very good to describe beam-like structures. We can use solid elements, we can use plate elements, and so on and so forth. There's a lot of possibilities. But anyways, every single element type is always connected to each other in nodal location. All right. So what we're going to do, let's say that this beam-like body, I'm going to change the color to make this a bit more clear. So let's go back to this color here. We're going to discretize. Let's see that we're going to discretize this by using plate elements. So it looked like a fishing net. So we haven't really discussed about the the plate element technology, but this is how it looked like. Now, this means that vector u bar f is unable to move in a million different ways, but it's going to be able to move in a certain different ways. With the certain different ways, or the limited number, infinite number of deformation modes, is described by vector of nodal coordinates. Vector of nodal coordinates telling that how is it when you put together all the degrees of freedom in each of the nodal location, how that vector look like. Okay, we do have an information about every single particle because if we go back to the single element here, this is a plate element. Every particle that is within the boundaries of this element can be described with help of shape function. Shape function is telling you how is that particles are assumed to follow this certain kind of deformation. What deformation particularly? That is a nodal degrees of freedom deformation. Deformation associated to nodal degrees of freedom. Okay, so back to this big picture. So now in this big picture, we have these nodal degrees of freedom. And in a nodal degrees of freedom, we can describe stiffness and inertia associated with this flexible body. Now the problem is that when using a conventional finite element, or let's say typical finite element procedure, the number of unknowns, this time vector of nodal coordinate, becomes to be very long. And that means that there's a lot of components in that vector. And that's a big problem. That's a serious problem because if the reference motion, meaning the large translation, is described by three components. The vector R consists of 6 components. Rotation matrix consists of 6 components. 3 components, of course. That means that there is going to be 6 or 7 coordinates describing the large reference motion. And now if this vector u bar here consists of very high number of variables, let's say 100,000, things are not matching well. So there are significant differences in terms of number of unknowns. So what we wanted to do then here is that we want to reduce the size of vector u bar f, this one here. And now for sake of simplicity here in this notation, there is no vector u bar, but just a u. Hopefully this is not making you too much confused. Okay, so what we're going to do then is that we're going to move from nodal coordinates to modal coordinates. Again, here's my advice to you. So when you look at these videos later, I find it out by myself that it's very useful to put these subtitles, these closed captioning on, because they're able to really nicely kind of read what is that I wanted to say. So next time, or when you're preparing yourself the midterm exam, make sure you're putting these close capturing on. And the close capturing is capable to recognize the difference between the nodal and modal coordinates. Okay, so we started from nodal coordinates. And for sake of reducing the problem size, we want to move on to modal coordinates. And the easiest way to make that happen is that we can conduct an eigenvalue analysis for this finite element model. In eigenvalue analysis, we are not solving absolute responses, but just the possibilities how the structure can deform. How you know that? You know that because in a model, in an eigenvalue analysis, to conduct the eigenvalue analysis, the force is applying here, the externally applied forces will be set to be equal to 0. So there's no forces applying in a system. So that's already telling you that this is all about the properties only, not absolute responses. And because it's a property, you're looking at how is inertia versus stiffness. Inertia versus stiffness. And once you conduct an eigenvalue analysis, then you can get these deformation modes, which are then related to eigenvalues. Eigenvalues are these resonant frequencies. You can make an interpretation like that. So that the resonant frequency is telling you what is vibration properties of the structure. Resonant frequencies are then in turn associated with certain kind of resonant deformation modes. Okay. Now, when moving on in this line, we can have this vector, the matrix, that is telling the relative ways how the nodal degrees of freedom can move. That can be then multiplied by modal coordinates. And we have this very important relation between the nodal coordinates and modal coordinates, and is related based on this deformation matrix here, which come from the eigenvalue analysis. Now, what happens when I'm moving from nodal to modal coordinates is this. So when I do this substitution, this is then substituted to my original equation here. Its original equation can be written like it is shown here. And this is very pleasant now, because if these deformation modes are orthogonal, meaning that they have no relation between each other, which is the case when you're conducting the eigenvalue analysis, then you can reduce the size of the problem significantly, but you can also get it in a mathematically more pleasant form. Mathematically more pleasant form comes from the fact that this one here is a diagonal matrix. This one here is a diagonal matrix as well. And they are diagonal matrices in a way that if you do the mass scaling, then the mass matrix associated to modal coordinates is an identity matrix. When you do so, then the stiffness matrix associated to modal coordinates is the one that the eigenvalues are located in diagonal terms. Other terms are equal to 0. All right, so that's how it goes. All right, so then a little bit of other things we discussed a week ago. So this is how in theory, how this eigenvalue analysis goes. So in practice, when you look at the commercial finite element software, they don't do it in this way. But for us, this time is okay. So it's enough for us to know that this is how the eigenvalue analysis goes. Now, again, super important observation is this. In eigenvalue analysis, forces applying in a system is 0. So forces are not accounted here. So it's all about how is a relation between the inertia and stiffness. And when I'm looking at this particular equation here, I know that there is an analytical solution which can be written like this one here. Once this solution is substituted here, the equation can be written like this. Now, what you do then is that you're first solving this part of the equation by solving the eigenvalues, which can be considered as these resonance frequencies of the structure. And once you know the resonance frequency, then you can combine associated deformation mode. So first, this guy here. Once you're done with that, you can substitute eigenvalues one at a time, this equation, and you can solve how is a corresponding deformation mode. Okay, and again, these eigenfrequencies, I'm sure you know what those are. So those are the kind of frequencies that if you're loading your, oh, what about the damping terms? This is really good. That's a really outstanding question. So what's going to happen to damping terms here? You know, in most of the cases when conducting an eigenvalue analysis, particularly here in the flexible multibody dynamics, we do not take the damping into account in eigenvalue analysis. It can be later taken into account when we are damping the deformation modes itself by introducing the damping that is related to and affecting directly to modal coordinates. But in eigenvalue analysis, we don't take that into account. But that's a good question. Like, what if we have a material that is with a really large damping properties? Would it be possible to take that into account? I don't know that. I think it can be accounted in a way, that the damping affects to natural frequencies, but it only started to affect when critical damping, which is like that, the values from 1 to 0 to 1, and 1 is a critical damping. It started to affect when the damping is like 0.3 or something like that, which you don't really see in a steel material or any kind of material that is usually used in engineering structures. But it's a good question, which my answer is that usually, does it create the complex eigen frequencies? Probably, but how to handle that in the case of this floating frame reference formulation, and how to handle it in this case. So that's going to be a question that I cannot answer to you. I haven't really thought about it that, because usually the assumption is that the damping is less than that value that affects to eigenvalues. And when you do that kind of assumption, you can easily ignore the effect of damping. But what if we could use some kind of like weird material like aerospace? In aerospace application, I'm sure you can find a material that the damping is huge. I don't know that. I have really never met the situation like that. Very nice. Very nice. Look at that. So you guys make me in a position that I'm unable to answer this question, which makes me feel good. Makes me feel good. I don't know how is that I can give you some kind of reward out of that. 1 extra point in class quizzes. Is that enough? I think it is enough, but outstanding question, which I'm unable to answer proper way. Okay. So back to this story. So I'm still in the summarizing how was the last week lecture. And now what I will do is that I will kind of like speed up a little bit, because the slides that I'm about to show you are the ones that we looked a week ago. But I need to tell you them to you one more time, because this example we looked a week ago, I still have like a follow-up story in that. That the story or the structure we looked a week ago was this structure that consists of 3 spring elements. And the spring elements is an element where each of the nodal location has just 1 degree of freedom. So it's capable to move in global x direction, or let's say that in element coordinate x direction in back and forth. So it can go this direction and it can go back. So there's a 1 degree of freedom in each of the nodal locations. So I have here 1, 2, 3, 4 nodal coordinates. So it means that my corresponding stiffness matrix will be 4 by 4, and my mass matrix will be 4 by 4. Okay, now I'm showing this kind of like classical way to conduct an eigenvalue analysis. So first I'm comparing my values by solving this part of the equation. So taking determinant out of this equation, and for sure you cannot do that in when the dimension becomes to be very high. But here I'm just for sake of demonstration telling how it goes for you. So I get the polynomial that is a fourth order polynomial. I can find the 4 places where the polynomial is equal to 0, and these are the eigenvalues. The first eigenvalue is 0, telling that there is no boundary condition in this structure. The structure can move as a rigid body back and forth. So that first frequency is associated to that. Okay, second one is a deformation mode we looked a week ago, and then the third and the second and third are also the eigenvalues associated to deformation. Okay, so now what we did a week ago was that we solved the eigenvectors associated to second and fourth eigenvalues. This can be, again, like in a hard way. It can be do it in a way that you substitute your eigenvalue one at a time, this equation, and then you're solving this vector here, which tells you how is the deformation associated to that eigenvalue. We notice that in eigenvalue number 12, the deformation mode is like this. Eigenvalue number 120 is like this. So those are the ways structure can deform. Okay, something we did not discuss a week ago was a mass normalization. The mass normalization comes from the fact that these solutions, these vectors, can be, now this one here, this vector here can be multiplied by any number you want. And sometimes it makes sense to multiply this vector by a number to do the scaling. You know, in a computer simulation, the numbers that are most pleasant are the ones that are close to 1. So if you have very small values or very large values, it's going to be hard to combine, hard to deal with those numbers using a computer simulation. So sometimes it makes sense to scale this vector here to kind of force the numbers to be as close to 1 as possible. And again, the reason is that that helps to make the accurate simulation. So then you don't lose accuracy because of the computer accuracy. Now, what we can then do is that we can use something that is called mass normalization. And mass normalization is the fact that I'm finding out the number which I should use to make mass matrix to be a diagonal matrix. So it's just like figuring out what kind of scaling number is most advanced to be used here. So now if I look at the eigenvector associated to eigenvalue 12 here, so this is an eigenvector. This is my mass matrix. This is my eigenvector again. I'm just simply multiplying that by the number that I don't know what it is, and setting this all to be equal to 1. Why? Because I would like to have my final mass matrix associated to my modal coordinates to be identity matrix. That's why. And when I'm solving the alpha 2 from this equation, so the alpha 2 is square root 1 divided by 5. Okay, so that's just the scaling. So it's not changing anything else, but just making the numbers to be more pleasant to deal with. There are other kind of normalization than mass normalization available. Some codes, some teams prefer to use stiffness normalization. And the stiffness normalization, of course, is the fact that instead of using mass here, you're using your stiffness matrix. Mass normalization is very often used. Stiffness normalization is proved to have certain advantages over the mass normalization. Like, again, the numbers are more pleasant to deal with. That's the advantage you can get. Okay, second mode, when I'm doing or redoing what I just did for the first, give me the second mode. I am, again, setting my deformation mode, multiply that by unknown parameter here, which will be solved here. Here's my stiffness matrix, and all that will be set to be equal to 0. This time it happened to be such that it was already scaled in a pleasant way, so the alpha is here 1. Now, when I'm putting together a matrix of deformation modes in a way that they are scaled or mass normalized already, this is how they look. So this is my first deformation mode, and remember the first deformation mode was something like, if the original structure was like this, it was stretching itself like this, getting longer and shorter. That was a deformation mode. Second deformation mode was something that, if I remember, yeah, let's take a look. So the first one was moving this direction, second this direction, this direction, this direction. It was like a wave traveling within this structure. Now, this is my matrix that tells me the way the structure can deform. So this is entire structure, how it can deform. And now this makes it possible to relate vector of my original nodal degrees of freedom, then this R, and then that's multiplied by modal coordinates. There's going to be 2 modal coordinates if using 2 modes, like shown here. 2 modes, because of the 2 deformation modes. Okay, now if I compute my new mass matrix and stiffness matrix based on these modal coordinates, mass matrix is going to be identity matrix like I was expecting to happen because of this mass normalization. As stiffness matrix, I have my eigenvalues in my diagonal term, nothing else. Right, so now if I would solve the problem using the modal coordinates instead of nodal coordinates, it will go like this. So I have here force applying in a system, and the force is obviously something that, you know, it's applying in my 4th node and in its positive direction like this. And I'm simply using 2 deformation modes instead of nodal coordinates. I'm using 2 modal coordinates, and those modal coordinates are the one that is associated to eigenvalue 12 and eigenvalue 120. So my equation of motion reads like this. Okay, so this is it. So then I can solve each of these 2 modal coordinates without, independently, so they are not coupled, because the mass matrix here and mass matrix here and stiffness matrix here are diagonal representations. They have no relation. The coordinates have no relation to each other whatsoever. And now it's possible to solve first modal coordinate and second modal coordinate, and then I can jump back to the nodal coordinates by using this deformation mode. And this is not in short, but this is in a nutshell how is this modal reduction technique. Well, kind of lengthy story, but this is what was it? I'll close the half an hour. You need to go back and forth number of times. Okay, then comes something a little bit surprising, and now you need to pay full attention to me. Okay, so something a bit surprising is this. Now, I want to take a look at the structure that is shown here, and this is structure that we know very well. So this is a crankshaft mechanism, and I wanted to model the connection rod, this one here, using a floating frame of reference formulation. And you see how it is connected to neighboring bodies, which is a crank here by revolute joint and a piston by revolute joint. So this kind of resembles as a simply supported beam boundary condition. But now comes the question. Okay, so if I wanted to create the deformation mode for this connection rod, how is that I should set the boundary condition, if any, in my finite element model? And the boundary condition in a finite element model means that if I have, let's go back to this spring mass system here. How is the way that I'm gonna touch attach this structure, this model here to ground? Or am I attaching this at all? So should I attach, using the reference condition? And the reference condition is telling you how this body reference coordinate system is attached to the body. Meaning, how is that I'm introducing the boundary condition when I'm conducting the eigenvalue analysis? Should I use no boundary condition whatsoever, meaning that the structure is kind of floating in a space? And when it is floating in a space, then this is how the relation between the reference condition and the deformation mode are looking like. Or should I use a simply supported beam condition? Well, this is a clear example about the simply supported beam condition. Or should I use a fixed boundary condition in a way that one end of the structure is connected to ground? Which is a correct way? Which represents the best situation here in a real structure when I'm combining this to my multi-body model? What do you think? What is it you think? So how to set the boundary condition? First method, which is floating in the space, simply supported beam condition, fixed boundary condition, or something else which is not showing in these three options. So which one is correct? Which one is correct? Okay, so let me see. Where is my... There. Here's my Socrative. We need to move that a little bit. No. Why? Why now? No, I think that I'm able to move it a little bit. Okay. Well, you're kind of like using the incorrect... Oh, here, it was simple that I thought. Okay, so here is my first in-class quiz. So how to set the boundary condition? Four options. Four options. But which one is correct? And here is my Socrative, and I got two answers already. And let me take a look at my YouTube studio. It seems that I have 13 viewers in my YouTube studio. So I'm expecting to get more answers. So what's the boundary condition? What's the kind of the way to set the boundary condition such that I can describe a connection rod in a crankshaft mechanism? Four answers. So it's slowly picking up. Okay, so six answers. So it seems that this is now the game is on, of course. What's going to be the success rate in this time? I'm thinking 100% because it's so obvious. Okay, what is that you guys are thinking? What the number is supposed to be? It's very quiet today. Okay. 11 answers. Okay, so soon we're ready to close. But what about the success rate? What is your prediction regarding the success rate? Okay, now it comes the number. So 88, 70. Yeah, so, but you're not with me. So no one is voting 100% other than me. Okay, so I got 11 answers. So the last ones, please speed up a bit. So soon I will close the case because I still have quite a bit of things to discuss today. So I want to move on. Okay, 12 answers, 13 viewers in my YouTube studio, so I guess that I'm good to go. Okay, so the answer is this. Each of these are correct. So the success rate can be considered to be 100%. Now, you did not worded that correctly, so that means that I'm still free of dancing and singing, so what are you gonna do? So it was, kind of like a tricky thing, but let me explain, like what, why? Now I'm confused. So to explain this story to you, let me go this slide here. And I made here a little bit of space because I need to do a little bit of drawings here. Now, what really matters is how this deformation mode look like. How is it they describe the deformation? And now when you actually look at them, each of them will look alike. So they are all having this kind of banana shape, and this banana shape is not so different versus one to another. And that's the only thing that really matters. Now, how they are attached to body reference coordinate system. This is what is this called this reference condition. Reference condition. And it's very surprising that each of them eventually will produce roughly the same result. So it's going to be roughly the same result. This is like very, very confusing. Like, what? How come, like, isn't it so that each of them has a different natural frequencies? Yes, each of them has a different natural frequency. So if you look at the natural frequency, it shows that this, and this, they are not same. But the deformation mode, they look pretty much same. Confusing. Okay, let's take a look. Let's take a look at, if I just model a cantilever beam using these three different reference conditions. Reference condition, let me first describe the cantilever beam in undeformed configuration like this. And then I'm going to load this cantilever beam on its free end. Let me use the first deformation mode. So in the first deformation mode, deformation will be something like this. Sorry that this is not so great drawing. But anyway, so this is how they look like. What happens in the case of deformation when you have this kind of reference condition is that your body reference coordinate system that was originally here will experience certain level of translation and rotation because it's going to move here. So it's going to go this location here, roughly. You see that roughly that's what happens. And now what matters to us is that we need to know this final point here, this point, this kind of like a free end, which is loaded here. And now if I travel this free end using first going, I need to change the color again. So if I'm going to use, let me put it in a green. So if I first travel here and then here, this is where I'm going to be. So this is where my free end is located at based on this reference condition. In this reference condition, as you see here, the body reference coordinate system, so this is representing the body coordinate system, is not attached to any of the material point of a structure, but instead it is floating with the structure. How much it is floating? Well, that depends on how much you experience a deformation and what is your assumed deformation mode. This is where the name, remember the main name of the method we are studying here is a floating frame of reference formulation. Floating frame of reference formulation. Yes, both ends of the structure are constrained. So we will get back to that. So they are constrained. This here too, I'm attached this, in this hypothetical case, I'm attaching that to using the fixed boundary condition to ground. But even if I had this fixed boundary condition, this body reference coordinate system is capable to move because it's a function of deformation. And because of the function of deformation, this reference condition is called floating reference condition. And this is where the name is coming from, floating frame of reference formulation. Floating frame of reference formulation. So it comes from this capability that the body reference coordinate system is not necessarily attached directly to the body. All right, so now there's an awful lot of stuff here, so I need to take some of them away to make this bit more easy to follow. Okay, so this was my first reference condition. What about the second? In the second reference condition, like this one here, yeah, in this reference condition, the body reference coordinate system is attached to material point, but is not following the orientation of the body, but it's doing the rotation based on the reference coordinate system. And again, when I'm moving here and then here, my final destination is same than here and here. So what matters is that where I'm moving in a final as my final destination. So that's what matters. And then my final reference condition, then this one here, the reference coordinate system is attached to material point and is following the rotation. Again, I'm going to the same location here. So that's why they roughly gives the same solution. Okay, what about this joint? So there's a revolute joint, and let's say that deformation mode is something like this. In the first, sorry that this is, let me make a bit better drawing for you. So let me take a better position here. So revolute joint, and I'm roughly describing, there's a deformation that is something like this. In this reference condition, my body reference coordinate system is again floating, like is shown in this picture. So it's floating with the body. And again, every single particle I scanned with respect to this body coordinate system. Here, the reference coordinate is like here, and again is scanned. So what really matters is final destination, not really the way you find the final destination. That's put it in a short. And this is where this possibility that you can use no boundary condition at all. So it's just the modes that are computed in a way that structure flows in a space. That's where the name, the floating frame reference formulation, is coming from. Okay. So I spent first 45 minutes. Let me see what else I have here. Okay, so it's roughly the same responses. Because in nonlinear dynamics, what really matters is your final destination, not what are the components before this final destination. And each of these, think about it, how you can go to this if you have a global coordinate system. In a global coordinate system, you go in this deformed location. They're all going to be roughly the same. And this is very, very surprising. Very surprising. What you cannot do then is that you cannot use multiple reference conditions in a one model. So once you have reference condition, whatever that may be, you need to be consistent. Okay, what about this? Did I answer well about this question which asks like, but in both end of the rod should be constrained. So when I was describing this configuration here, when I have this revolute joint, still when I'm using these modes, my body reference coordinate system is floating. And the floating means that, it's a function, the way it's attached to the body depends on how is that you select in deformation modes. How much it is floating depends on how much each of these modes are actuated. How much does each of these modes experience a deformation. That in short. Confusing. It's like, okay, I'm going to get the headache to think about this. And this is not simple. For sure, this is not simple. But again, go back and forth in this particular recording, and I think that all that becomes to be clear to you. All right, so that was my kind of like theoretical thing. And let me see what else I have. Okay, this is something that I definitely want to test this. Okay, what the floating means in the floating frame reference formulation. It means that the formulation is still under development. It means that the body inertia can fluctuate. Body inertia can fluctuate. Body inertia can change. It means that the strain within the flexible body can be defined easily. It means that the body reference coordinate system can move from a material point of the body. And the competition is on. Okay, shoot it. And I want to show the how is a circuit for you. Here it is. Or maybe better to put it like this so you can see what are the options. How is the success rate in this time? No answers for that. Okay. 100. Nice. Very nice. Okay, and let me take a look. So I got 3 answers so far. So there's a fairly low number, like 65. I'm also thinking that this may be 100%. 100%. So my voting is this. 100%. Okay, so and let me take a look. So I got the 4 answers, 5 now. And I know that there's always I think it is like 15 seconds delay, whatever I'm saying and whatever you hear. Huh. Okay. Kind of funny thing happened to my YouTube studio. It was like I lost half the page, like it was cut in half. that never happened before, but now it look okay. Okay, so I got 10 answers, and last time we got 12 in total. So I'm gonna wait a couple more minutes, and that's about it. Okay, 15 viewers, so it's more than usually. Not much more, but a little more than usually. So here's my in-class quiz. Okay, so last one's voted, and then we're gonna close this game. Still some complaints about my audio stream. Something that the audio is not perfect. Anyway, so I got 12 answers, and I guess that I'm not gonna get more than that. So here it is. So here are the results. 92. 92. So that's really good. Really nice. 92. So let me take that away and let me take a look. So do we have a winner? And again, kind of weirdly, like half the page disappear. Oh, okay. Now it looks okay. Okay. So do we have winner? Well, we have 91. 91 is close enough. So we do have, we have 93. 93. Good. Good job. Okay. Back here. Now I know that I already spent more than my first 45 minutes. There is still a material that I kind of would like to include to my midterm exam, but I guess that I will shortly explain this to you. And now I really would like to use all my skills to make this as clear and as understandable as possible. What I would like to include in a written or midterm exam is this Crankshaft method. Why? Because the Crankshaft method is very heavily used. And that's simply because, we concluded earlier that you can use whatever boundary condition you want. So everything kind of goes. But in real life, many of the ways when using the boundary condition is difficult to use in practical applications because most of the practical applications, the deformations of the structure are not symmetrical, but instead they are heavily unsymmetrical. So just to give you an example, so there could be, this structure you guys are dealing, I think that's a good example. So this is a beam-like structure like this, which is loaded in the end. And then there is a revolute joint here, and there is a force here. So probably the deformation modes are something like something like this. So there is a kind of heavy local deformation at the point where the hydraulic cylinder is located at. And that makes it difficult because most of these eigenvalue modes, or modes that are coming from eigenvalues, are kind of symmetrical. And it becomes to be increasingly difficult to describe this kind of local deformation regardless how many modes you're using. So then there is an alternative. And this alternative is Crankshaft method. And the Crankshaft method is a method that is like a tool that can be applied almost all the problems you want. And it's a tool that is computing these deformation modes in a kind of clever way. And the kind of clever way goes in like this. So you take your structure, this time is like plate structure like shown here, and you're dividing your nodal coordinates in your structure to two different categories. So first category is called boundary mode, and those are the modes that those are the locations where you're expecting that there's some kind of local businesses going on, local deformation, local strains, local stresses you're interested, and you wanted to look closely what happens there. Roughly speaking, or as a rule of thumb, these boundary DOFs are locations where there's either a joint or there's a force applying in the system. Okay, so you're selecting the number of degrees of freedom to be boundary degrees of freedom. Rest goes automatically to interior degrees of freedom. Interior degrees of freedom, which is the rest. So clicking, okay, this is where the joint is, this is where the force is, and that's it. No further actions needed. Then automatically your commercial finite element software will rearrange its stiffness and mass metrics and associated nodal coordinates in such the way that the boundary degrees of freedom will be moved to upper left corner of your stiffness and mass metrics, and the boundary degrees of freedom will be in the beginning of your vector of nodal coordinates. Rest will follow. So this is rearranging, which you are okay to do. So you can, of course, do this rearranging. Once the rearranging is done, then you take a look to, if going back here, to this part and this part, which is just the interior nodal degrees of freedom, nothing else. Interior nodal degrees of freedom, and you're conducting an eigenvalue analysis for those submatrices. Interior degrees of freedom and eigenvalue analysis. You will get the modes that are associated to interior degrees of freedom. Okay? Then you take a look to your stiffness matrix, this one here, and from your stiffness matrix, you are solving these interior degrees of freedom. You're going to get something that is called static correction modes, which are heavily emphasized by this local deformation. I'm going to give a drawing. I will give you drawings in a minute so you will see how they look like. Okay, then you're combining these deformation modes. And then, how are these deformation modes? First one here are the ones that it's associated to this interior degrees of freedom. And interior degrees of freedom goes like this. So I have beam-like structure, which is, I'm selecting this one here, the node in the middle, a node in the left-hand side to be my boundary degrees of freedom. And now my first set of modes, which is called fixed interface normal modes. What a monster, no need to memorize that. I'm computing the eigenfrequencies in such a way that each of these boundary degrees of freedom are attached to ground. So they're fixed to ground. And the rest of the degrees of freedom, they can fluctuate based on the eigenvalue analysis. My another set is a static correction mode. And the static correction modes are such that I'm introducing unit displacement to each of these boundary degrees of freedom one at a time, where rest of the boundary degrees of freedom are with no deformation. So that's my static correction modes. And this is it. So I'm combining these two modes, my free modes, or my, what is this name again, fixed interface normal modes, and my static correction modes. This is it. So that's how it goes. And now you can apply that to a wide variety of applications because it's kind of flexible to handle local deformation and also this global deformation. So that's the advantage of the method. There's a minor beauty mistake, if you may. The beauty mistake is the fact that the static correction modes, because they are based on unit displacement, they are not orthogonal. And that means that if you compare the new stiffness and mass metrics, they're not going to be diagonal representation because the one set of the modes is not orthogonal. This you can fix by simply conducting an eigenvalue for these matrices again. Okay, so let's do it. And once I do that, then how they representing the situation will change quite radically. But now I eventually am able to get these deformation modes that are orthogonal. So that's a great Bunch method in short. So let's take a look. So you get started by first selecting boundary degrees of freedom. Let's say this one, this one, and this one. And then you're attaching these boundary degrees of freedom to ground. You conducting the eigenvalue analysis for rest. So you get the deformation mode where these locations are fixed in a ground and their other degrees of freedom are fluctuating, vibrating as they can. Then you have another set of mode, which is a static correction mode. And in a static correction mode, each of the boundary degrees of freedom are actuated, or that you are introducing the unit displacement to them one at a time. One at a time. You putting them in a one package. You are recomputing the eigenvalue analysis, which is called this orthonormalization. You get the modes that are roughly free modes, and something that there is a very heavy local deformation. And now you're done. Very short news flash. Very short news flash. Sorry that I was this much in a hurry to explain this to you. So I only spent 10 minutes, I guess. Okay, now back to another presentation. Let me see if I have any comments. No comments this time. This one. Right. I guess that I need to change my window here. Okay. All right. Now, like I mentioned in the very beginning of today's lecture, yesterday I was checking from these, I don't even remember the name of the website anymore. But anyways, one of those websites that you can check how is lecture schedules and how is an exam schedule. And I checked like how is a midterm exam for this course. And I was unable to find it. Honestly, I was unable to find it. I don't know if it was me or if it is something that there is nothing mentioned about the midterm exam. So that was very confusing to me. And now I'll need a little bit of your help. So if you know that there is a midterm exam scheduled for this course, please let me know when it is. Because then I thought that, okay, let me make your proposal. So let me ask if this time is okay to you. So first of all, the exam will be organized in Modal. So again, you can keep all your material with you. So So you can do the exam similar way than in a simulation of a mechatronic machine. But the difference this time is that you only have one certain time window to do the exam, because I don't have a question bank this time available, and simply because there is just a handful of questions that I'm about to ask from you. What are these questions? Those I will show you momentarily. But anyways, my question to you: how is Thursday, March 3rd at 4 p.m. to 7 p.m.? Is that time okay to you to participate to midterm exam? To participate the midterm exam meaning that you need to be in front of your computer that have an access to internet, and then you go. And you will have, like mentioned here, 3 hours time to do this exam. So how that sounds? Two questions to you. Do you know if there is something mentioned about midterm exam somewhere in the university official website? And if nothing mentioned, if in that case, is this time that I just proposed to you, is that okay to you? And now I would like to hear your response. And the way you can communicate with me is this chat, of course. Let me see if, because the only thing that I was able to find was this final exam, nothing else. But I don't know, maybe the website is different now. That's another thing that I'm not sure. So please help me. Where can I find the exam dates? Okay, so you guys are not willing to communicate with me today. So the time is okay. Okay, was there anything mentioned about the midterm exam? Because the only thing that I was able to find was this one. And I will take a look at your, what about others? So is it, I just got the one feedback that the time is okay, but others, is this time okay to you or not okay? Okay, so this was a website that I was able to find. And now here, this is in Finnish, but I'm gonna check here exams and midterm exams. Okay, then, oh, I think I was looking in the wrong place. Oh, hey, my mistake. I think now I'm able to find it because I was looking in the paper exam, and this is not the paper exam, but something else. Here is a, but it's not here either. This is not, what about this one? No, not this one for sure. This was the only thing that I was able to find. Oh, this is not the good way to show it to you. Where is it? Simulation laboratory course, and it only says final exam. Okay, now let me know if this time is okay to you, what I just proposed, and let me show that to you one more time. So this is what I'm proposing. So the exam will be organized in Modal on Thursday, March 3rd at 4 p.m. I got 2 responses which says that is okay. Others, let me know. Yeah, so it seems that it's simply missing. So there is nothing mentioned about the midterm exam date, which is a big surprise because, don't know how that happened. But I got this third confirmation that this time is okay to you. Okay, others. So I got fourth, it's okay. All right. So while you guys are checking your calendar, let me show you what are the questions I can ask. And as promised in the beginning, so there's going to be a voting action prior to midterm exam. So it's going to be voting action this week where I'm asking you two things. I'm asking what question you for sure would like to see in written exam, in the model exam. And once you're voting something, I will definitely put that question to midterm exam paper. And I will let you know in advance what question there will be for sure in that written paper. Okay, so yeah, what kind of question is? These are the questions that I'm asking. So if you take a look at the slides, these are the kind of the questions. So they're all like essays. So there is a short explanation I'm expecting you to offer. Short explanation, but thorough ones. So don't start to explain about how is your summer and how is you been busy this winter. Those are not related to any of these questions, but you explaining everything you know about this subject matter. That would be the way to go. And again, questions are listed here. So first set of questions is shown here. There's going to be more. There's going to be more. These are the first 11 questions. And then I also have these star ratings, meaning that if you're busy, what are the questions and what are the topics that I'm hoping you to focusing on? So three-dimensional kinematics as a big picture, medium importance. So it's rated as a 3 stars. So it's not super important, but it's something that definitely if you want to score, I would say 4 and 5, maybe even 3, that's just something that is heavily recommended to do. To kind of master this particular topic. There's certain topic within this three-dimensional kinematics that are more important than others. Rottiquist equation is one example. Erlo Parameter is another example. So if nothing else, make sure you understand the concept of Rottiquist equation. Don't memorize this equation. No, not that. But memorize how the story went. That you have, once upon a time, you have this vector R. Then comes his friend, vector V, which is unit in a length. And they made a team together. And then there was a rotation that was introduced around the vector V, that was again unit in a length. Because of the rotation, the vector R was changing its position. And then you can describe mathematically how this relation can be defined. And that's your 3x3 rotation matrix. Make sure you understand what this skew-symmetric representation means and what are the 4 parameters used in this description. And those are components of vector V and angle theta. Now vector V is unit in length, and because unit in length, that's your constraint. So there's only 3 independent parameters here, because 4 minus 1, that's 3. Okay, Erlo Parameters is kind of an extension of Rottiquist equation, so you're just calling the parameter components in different names. These are the name tags. So using these name tags, you get your Erlo parameters as it is shown here. So simple like this, very, very simple. And mathematical properties of rotation matrix, not very important. Comparison of different methods, yeah, that's kind of like more than medium importance, Robot kinematics, like again, 4 stars, so make sure you understand the concept itself, you understand how this goes here. By the way, the instructions how to answer these questions, that will be offered to you also during this week. So I'm going to explain how is it you can answer these questions, how is it you can maybe use some drawings and so on and so forth. So all the details will be available for you a little bit later. So I was here in the robot kinematics. So in a robot kinematics, when you have there's a 4x4 matrix representation, which is heavily used. So you take the components of kinematics using a multi-body system dynamics. You're relocating the R to be in the upper left corner of this 4x4 matrix. Rotation matrix is going to be upper left corner. And this is it. That's all that is need to know. Why this is important? Because it helps you to describe the kinematics. It really helps you to describe the kinematics of robotic systems. And one of the method that is heavily used is this Hartenberg method, which is based on 4 parameters, predefined parameters. And it goes such the way that these parameters are the ones that are shown here. So they define the different properties that you often see in robotics. And once you have these 3 parameters, then you can model the kinematics in a way that you can simply build a table or matrix. I think that this is more table rather than a matrix. Each of the rows in the table tells how is it different bodies, and the columns of the table telling what are the components, what are these 4 Hartenberg parameters associated with this particular robotic system. That's it. That's kind of a nutshell how this goes. Velocity of particle, meeting importance. If you understand the nature of the G matrix, that would be outstanding. That would be really a lot. That would be a lot. And the nature of the G matrix is that relates angular velocity vector and this theta dot. Theta dot, which is a time derivatives of your rotational parameters. And this theta dot, theta in the first place consists of 3 or 4 parameters, depending what is your rotational description you use. Okay, so then more questions, how inertia tensor can be related to acceleration of rotational generalized coordinates. So rotational generalized coordinates, I think this is the right way to go. And this is again, with help of G matrix. So you need to be able to understand the nature of the G matrix. And here it is again. So here's your inertia tensor, which is then mapped, whatever representation you use, with help of G matrix. So that's it. That's it. Now, moving on, these are the details. This was the equation of motion. I don't think there's any question related to that, so you can easily skip this particular part. Then simple questions related to flexible bodies, like a big picture, why deformation needs to be accounted, how linear strain displacement relationship affects, explain the concept of lamp mass approach. So those are not too complicated at all. This is a lamp mass approach where you take your original body, you divided your original body to number of rigid bodies, and you are attaching spring elements between these bodies. By the way, something that I think that I have not explained to you, but what happens after this week 8? This was week 8. Next week is a midterm exam week, and we're gonna have this midterm exam on Thursday. And then when we're coming back after this midterm exam week, there will be a lot of visiting lectures. So there's gonna be visiting lecture about the biomechanics. I think it's gonna be quite a bit of fun for you. There's gonna be visiting lecture about bicycle dynamics, which is outstanding. There's gonna be and vehicles as well. So vehicle dynamics and bicycle dynamics in particular. There's going to be a visiting lecture about BLM systems. There's another visiting lecture about, don't remember what was it. But, this is when we're going to start looking things in real life. Because I got these complaints, okay, yes, partial this, partial that. But how this is related to any of the real life. And the real life you guys are referring, of course, how is life in industry. So that will be tackled in our next period. Now back to this. Floating frame reference formulation, general idea that we have this vector u bar 0, vector u bar f, how it goes. Comparison of different methods, relatively important. More questions. Explain how polynomials can be used in the approximation of displacement in finite element method. Role of Pascal's triangle, what the convergency rate means. Each of these matters are explained to you. And more, what the safe functions are describing, how to obtain the safe function matrix, physical interpretation of eigenvectors, eigenvalue, how to conduct an eigenvalue analysis, mass normalization. What the reference condition means in a floating frame reference coordinate. floating frame reference formulation. And the reference condition means that how do you set the boundary condition when you're defining these modes. That's what it is. Is it floating? Is it fixed? Or is it something between? Like simply spotted beam or something between. So that's what tells you the reference condition. Okay. So that was a question ID 25. So finite element method, polynomial expansion. This is important. So this is very, very important. So you understand that the nature of finite element method is all about the polynomials. And you might have wondered, like, why polynomials? Why not something else? Why not just use, for example, trigonometric functions? Because those two you can differentiate easily, so they are not difficult to use. And the answer is that still the mathematical behavior of the polynomials is superior. The trigonometric functions are not capable to introduce kind of like a complex deformation modes with which polynomials are capable to do. And now, just shortly, I don't know if you guys are still paying attention to me, but I think that I mentioned earlier to you that the polynomials is like an obvious choice. But if you're not happy with that, you can use a B-splines or even non-uniform rational B-splines, NURBs. NURBs are the ones that are heavily used. NURBs. NURBs are heavily used in CAD geometry, and it kind of helps to combine finite element models and CAD geometries. And when you do that, then there is a method that is called Isotrometric finite element method, which I will get back to that in fourth period. But yes, there is a possibility to get rid of these polynomials if you hate them big time. You can use something different, like B-splines, non-uniform rational B-splines, but then you can make any kind of geometries you want. Okay, so that's like the nature of the finite element method. And what you do then with this nature is that you replacing these unknowns, which are called polynomial coefficients, by not a degrees of freedom. Why? Because these polynomial coefficients, they don't have a clear physical interpretation, whereas the not a degrees of freedom, they do. So it kind of makes it more user-friendly or human-friendly, put it in a short. You could use these polynomial coefficients, not a problem, but it's kind of against the human nature and human thinking a little bit. But yes, you could. How to derive the stiffness matrix? Don't take a look at that. These are the safe functions, so they are based on polynomials. Remember that. They are based on polynomials. Again, you can get them by replacing these polynomial coefficients by not a degrees of freedom. And solution techniques for equation of motion. So you can solve that directly, or you can move to modal coordinates, from nodal to modal coordinates. And when you do that, then you can get two benefits. Most significant benefits is the fact that you can reduce the size of the problem. Another minor benefits is the fact that you have diagonal representation, which is more pleasant to solve. Okay? Eigenvalue analysis, we discussed that shortly. Make sure that you understand this nature of the model reduction. This is so important. And for sure, there's going to be a question related to that. Then there's a Craig-Bampton approach, which we shortly discussed. The next one was not there. Okay, here's a question that there's a high chance that you can find in the exam paper. And it goes like this. In the finite element method, equation of motion, equations of motion. I can see there's quite a bit of typing mistake here and there. Equations of motion can be described in terms of nodal degrees of freedom as follows. Number of variables in the equation above can be reduced using a modal reduction technique. Explain how it goes. Then the kind of question that I like, where the word floating is coming to the floating frame of reference formulation, what the floating is standing for. Deformation mode in the floating frame reference formulation can be obtained using Crankshaft method. Explain the procedure of that method. That's it. That's it. And then the final one, remember to have this can-do attitude. So that's why the person we're following, the role model for us is not Lagrange, not any of those mathematicians that are super famous, but Elvis. Why? Because what matters end of the day is a can-do attitude more than anything else. So remember, can-do attitude. This is, again, highly theoretical, but as promised, the next period is all about, well, not all about, but quite a bit about to get to know about the different practical applications, get to know about, bigger picture related to simulation. And that's why those visitors will be coming with us. Another thing that is a little bit unclear to me is how we're going to conduct these visiting lectures. Some of the visiting lectures are far from us. Like the vehicle dynamics, this bicycle dynamics will be delivered by a professor that is in Delft University of Technology, and that's in Netherlands. And that's really far from us. And probably, that I don't know for 100% certainty, but most probably the lecture will be this YouTube lecture like the one today. Then the biomechanics, I need to check how are the rules from university administration. Maybe it can be face-to-face discussion. Again, I don't know that. The BLM, that I don't know. But anyways, I'm going to take a close look about the instructions during the exam week, and I will keep you posted. I will let you know. Okay. Oh, look at that. I was fast. It's still, I have like 9 minutes to go. I don't know if there's any questions, comments. I just would like you to be aware that, again, there's going to be this voting action where you can vote one question out of the 29 questions, which for 100% certainty will be in exam paper. You can also take one question away. Again, one out of the 29 you can vote off, meaning that for sure it's not going to be the exam paper. Then there's going to be, the one you're going to select, and I will select 4 to 5 other questions. So there's going to be a total of 5 or 6 questions, which are the questions you just saw. So that's how it goes. And again, remember, exams are just a half from the course in total. The other half is about how is that you're doing in Suraj's case, and how is that you're doing with the simulation exercise. But now, I know that the communication is not fluent, but if you have anything in your mind, anything you would like to ask from me, other than the stamping, which I was unable to address in a proper way, use a chat window. No, we have no lectures next Mondays because next week is about is an exam week. So the idea is that you guys just fully focus on the exams. No lecture on what is it, 29th of February. I think it is the last day of this month. No lecture on Monday. And I will send you an email to explain the situation. Okay. Anything else? Any other comments, questions? And I know that there is this pretty serious delay, so that's why I'm gonna wait a while to see if you have any doubts. Here's again. Here's the exam date and time. And again, you will see this later in Modal that there is a separate page exam that will be open for this time. You may use less than 4 hours time, but if you're coming, let's say Friday to do this exam, so it's not going to be available anymore. So this is a time window that you need to do it. Okay, but again, let me know. Okay, and 3/3 is, what is this? 3/3 is not next week, but oh yeah. There's a third of no, it's next week. Next week is a March 3rd. So take a look at the calendar. So it's not this week Thursday, but next week Thursday. So because next week is again the week that we have no lectures, that we have no other activities except exam, midterm exam, to be more clear. Yep. All right. Okay. So that's about it. Okay. So if no other comments, questions, time is up. So I'm gonna close this streaming, and I will see you. Let me tell you when we're gonna see then. So it's gonna be uh, Monday, uh, Monday, March 7th at 8:15. You know that the streaming is always getting started at 8 o'clock, but the lecture will be on at 8:15. So see you then. Have fun. Take it easy. Have a can-do attitude, and see you in 2 weeks' time then. Oh, yeah. See you in 2 weeks.